Hello everyone, this is our sensors and transducers lab. So in this lab, in today's session, we will discuss how to measure a linear displacement using Lvdt, right? So let's see. Here the aim of our experiment is to measure the linear displacement using Lvdt. Then apparatus required. So for this experiment, we need some apparatus or components which are multimeter, DSO, wires, and the most important is Lvdt measurement kit, which is developed by or manufactured by Syntec. So it is Syntec 2303 Lvdt trainer kit. So what is Lvdt? Lvdt is linear variable differential transformer. So in this Lvdt, there is a moving iron core. You can see here, and one primary coil is there or primary winding is there, and two secondary windings are there. This iron core will be moving. So whatever position of your object, whatever you want to determine or measure the position or displacement of an object which will be attached to this moving iron core. So this primary winding, the AC current will drive this primary, and an EMF or voltage will be induced in the secondary winding, secondary coils, right? So by measuring this EMF or voltage, this is a signal conditioner circuit, and after that a differential amplifier is there. So whatever signal will produce in the output, that means in the secondary coils, that will be passed through this signal conditioning circuit, which contains some rectifiers and filter circuits inside that, and after that it will pass through the amplifier, right? So amplifier will amplify the output signal or output voltage, whatever we will get from here, and give us the final output here. That will be measured by using the multimeter, and we will see, as well as along with this measurement, we will observe the output of this Lvdt in the DSO. This is our DSO, which is digital storage oscilloscope. Here number of channels are available. So in these channels we will observe the output of that Lvdt, and various options are there. So from these options we can easily get the data of that measurement of Lvdt, or whatever graph it will display, the data of that graph we can easily obtain by using these options, right? So this is the diagram. This is the iron core. The motion will be like this, like linear displacement, and primary coil and secondary two coils are attached here, and the object, whatever displacement you are going to measure, it will be attached or interfaced with this moving iron core, and the AC current will drive the primary, and as I said earlier, the EMF or an EMF will be induced in the secondary windings. So from these secondary windings we will measure that means these two secondary windings, from these 2 points we will measure the voltage difference or EMF by using multimeter, as well as we can see the output in the DSO also, right? So AC supply will be provided here. So this is the whole internal structure of Lvdt, right? So in this kit we are going to perform the experiment now. So let's begin with the experiment. So this is the iron core. Inside that, the moving iron core is there. So here you can see this is the micrometer, which is having plus minus 10 mm of displacement, right? Plus minus 10 mm of displacement, and here you can see from 0 to 10, 0, 5, 10 and onwards it is 15 and 20. That means from 10 to 0 it is 10 centimeter in this direction, and that means backward direction, and from 10 to 0 it is 10 mm in backward direction and 10 to 20 in forward direction, it is 10 mm. So it is a total of plus minus 10, that means total of 20 mm displacement, right? So initially it is in 10, that means it is at null position. We are taking this 10 as a null position. So let's see at null position what is the output. So this is our multimeter. It should be at voltage, and we are connecting the multimeter to the output side, and we are turning on the supply. So here you can see it is at null position, and the display for displacement it is 0. That means the Lvdt iron core is at null position. At 0 it is showing 0.654 volt DC. So it may vary slightly. You can see it takes few seconds to be stable. Here it is showing 646 millivolt, that means 0.646 volts at null position, right? So this is the DSO where we are using 2 channels to observe the output. For channel 1 we will connect it to the primary windings in this, and channel 2, that means this one, we are going to connect it at the secondary ones, right? So before that the ground connection should be made. So the ground connection we are making with this wire, it is at ground. So now ground for channel 1 and as well as channel 2 will be connected here, right? Okay, it is done now. So this is channel 1 probe, which I am going to connect here to observe the waveform, and this is for channel 2, which I will connect at this point. So initially you can see this is channel 1 and this is channel 2. At channel 1 it is connected to the input AC, which is showing the waveform, and this is the output whatever we are getting at the secondary ones, right? So now this is at null position. So now I am going to freeze it and just adjust this to okay. So this is at null position. So at null we have initially got the output as 646 millivolts. So now I am going to increase this using this micrometer. That means I am going to make a displacement of that iron core. So from 10 after every 2 mm I am going to take the reading. This is at 8 mm, right? At 8 mm. So at 8 mm it is showing the displacement as 2 mm. That means from 10 to 8 it has been displaced by 2 millimeter, and the output it is showing 621, right? You can see this is the output, right? So now I am going to make it 6, that means 2 more millimeters. You can see it is at 6 mm, right? And the output it is at 6 mm, and the output is showing as 602 volt DC, right? Here you need to note down the Vmax from here also for channel 1 as well as channel 2. You can also take down the readings. It is 2 volt and it is 500 millivolt, and channel 2 it is showing here, but the output we are getting 604, 602 or 4, it might get some fluctuation, 604 millivolt, right? So as so on we increase the displacement more towards the backward direction, this is at 4 mm and the display is showing 6 and the multimeter reading is 584. Okay, so as we have increased the displacement from 10 to 0, I have just shown here 10 to 8, 8 to 6, 6 to 4, then 4 to 2, then 2 to 0. So this is the final one. I am just showing few of these readings, how to get those outputs and how to measure the displacement using this kit. So here at final position at 0 position, that means from 10 to 0, that means it has been displaced by 10 mm, which is showing here in the digital display of 10 mm displacement, and the output in the multimeter we are getting 548 millivolts or 0.548 volts. So now we are going to see from 10 to 20 few of these readings, right? So coming back to null position, it is again the displacement is showing as 0 mm, and here the output, which was initially we found as 646 or 645 millivolt or 0.645 millivolt. Now I am going to make the displacement in this direction. From 10 to 12. Here it is at 12, right? It is at 12 and the displacement is showing in the digital display as 2 mm, 2 mm displacement it is showing, and the output whatever we are getting in the multimeter, it is 0.666 volt or 666 millivolt. So here you can see it is showing minus because initially we moved in this direction from 10 to 0, so it was showing as positive displacement, and from 10 to again initial position from 10 to 20 it is showing that negative direction. So the minus sign, it indicates that the displacement is in opposite direction, right? So that means the iron core is moving like in this direction, it is going forward, right? So here now 12 to 14, here you can see it is showing 4 mm displacement, and it is in position of 14 mm displacement, that means 10 to 14 which is 4 mm, it is showing minus 4, and here it is showing the output as 687 millivolts, right? So likewise we will move forward from this 14 to 16 and 16 to 18 and again 18 to 20. So the final reading will be at 20 mm, which is nothing but 10 mm minus 10 mm of displacement. So here it is at final position, that means at 20 mm, and the micrometer position is at 20 mm, and the displacement is showing as minus 10 mm of displacement, that means from 10 to 20 which is 10 mm. For this 10 mm displacement, whatever the output we are getting in the multimeter reading, which is 744 millivolts, right, or 0.744 millivolts. So likewise we can measure a displacement of total 20 millimeter, that means plus minus 10 millimeter, total of 20 millimeter displacement from 0 to 20 we can measure using this Lvdt kit. I am showing you for various other Lvdt instruments, the range may be vary, but in this kit it is for plus minus 10 mm displacement. So for this 10 mm displacement, whatever output we are getting in terms of voltage I have shown. So now, so as we have got the outputs for few observations, so this is the observation we have got for 10 mm, which is we have taken as null, that means display position was at 0 mm, we got 643 millivolts. The output is in millivolts, 643 millivolts, it is at null. Then at 8 we have got the display position at 2 or 2.1, it may little bit vary, but it should be in the tolerance level, tolerance band, not so much error should be arise here. So here it is showing 623 millivolts. So the output, actual output whatever we have got is 643 minus 623, that means for this 2 mm displacement or 2 mm movement of that core, we have got 20 millivolt output. This is the actual output, and here at 6 mm we have got 3.9, that means around 4, which is 4 mm of displacement of that iron core. We have got 604 millivolts as output. So for this 4 mm displacement, the actual output is 643, which was at null position or the reference. 643 minus 604, which is nothing but 39 millivolt. That means for this 4 mm displacement we have got 39 millivolts of output. That means the induced output, induced EMF or voltage which has been occurred or induced in the secondary one, is 39 millivolts. So likewise, the other readings we have found here, we can see after the reference level, that means at null, we have, whenever we have go for the backward direction, that means at 12 it shown 2 mm of displacement, 2 mm or 1.9, whatever we have got, the output was 663 or 664. So the actual output is of 20 millivolt. That means for backward direction also, for the movement of 2 mm it is showing 20 millivolt, and for 4 mm it is showing 41 millivolt. Here it shown 39 millivolt. So these outputs for positive displacement and negative displacement, both should be the values should be the nearest value of this should be equal, almost equal. This is 20, this is 20, or this is 39 for the forward, and this is 41 millivolt for the backward direction. This is 59, this is 61, likewise 78, 79. So this is the positive displacement and this is the negative displacement, and from these readings we can prepare also a graph like this: sensor position and output voltage. So sensor position from 10 to 0, 10 to 20, so whatever voltage we are getting for the positive displacement and for the negative displacement as well. So we can prepare the graph in this manner, right? So this is all about the measurement of linear displacement using an Lvdt kit, right? So few more sensors are there by which using which we can measure the displacement. So this is one of them. So this is all about the experiment. Thank you.